Welcome, I'll be showing you how to get set up and running with pyTorch on the Queen Mary Andrena GPU cluster using a virtual environment with pip in just a few minutes. We'll walk through the steps in the process, we'll connect to the login node using SSH, create a virtualenv environment, and install our packages into it with pip. Then, we will download some example Python code that uses pyTorch. And afterwards, we'll create a job script to tell the scheduler the requirements for our job. Finally, we'll run the job and check the GPU activity and inspect our results. So, we're going to start off by connecting to the login node, which is where jobs are submitted from. The information that we provide here is available on our documentation website. So if you have an active login account, you can connect to andrena.hpc.qmul-its-research from a terminal session. And here you can see on the SSH command, I've included my username on the cluster. Enter your password and you're connected to the front end. Now, once you're connected to the front end, you can do all sorts of activities. I'm just going to quickly check the status of the Andrena nodes. And here we can see in this instance, all of the GPUs are being used. For compatibility reasons, we assign 8 cores per GPU. So if 32 cores are being used on these nodes, this means that all 4 GPUs are occupied. So once we're logged on, the next step is to load the Python module and then create an environment whereby we can install packages, and then finally we'll install the packages that we need. Okay, firstly I'm loading the Python application into my environment. I use the module command to do that. The next 2 commands aren't essential, but I'm just doing it to demonstrate the effect of loading the module. Then we create the empty virtual environment. I first change directory into the place I want to install it. Then I use the virtualenv command to create a virtual Python environment called pyTorch-env, where I can install the Python packages. Now, before I actually install packages into the environment, I need to activate the environment in my current session. You can now see that the prompt has changed to show the name of the environment that has been activated. Now finally, to actually install pyTorch into our environment, we follow the instructions on the pyTorch website. We've selected Linux, pip and CUDA 11.6, and we can copy and paste this command into our active environment, and the installation will take a couple of minutes. I've sped up the sequence a little bit here while we're waiting for the packages to be installed, but note that CUDA Toolkit is not installed as part of this process when we use pip, so we have to additionally load the corresponding module when we run our job later on. The installation is completed, so we can do a quick test to see if the packages have installed okay. Just for demonstration purposes, I also ran the pip freeze command to show the packages that have been installed in the environment. With our environment still activated, we can run the Python command, then import the torch package, and it should load successfully with no errors. This is not a full test of the GPU functionality, but it is a very basic test to confirm that things have generally gone okay. To run our code on the cluster, we need to create a job script, which specifies the kind of resources that we need to run, and then it also specifies the commands that will be run. And if we're testing pyTorch, then we need some code to run on the cluster. I've created a directory called pyTorch example, and it's just empty at the moment. But in a repository on GitHub, I've got some code that I'd like to run. So first I'm going to download that code, then afterwards I'll be creating a job script. I've clicked on the file in GitHub, then I've clicked on the raw button so I can get the pure code. I can use the wget command with that URL to actually pull the file down onto the machine. Alternatively, of course, I could have just copy and pasted the code from the raw view into a text editor. Anyway, the result is just the same, and here I am just checking that the download works successfully by opening the file in a text editor. In order to run our code, we'll create a job script which specifies the resources we need for our job and the commands to be executed. And you'll find on the Andrena page of our documentation website, there's an example job script which is ideal for this kind of job, so let's copy and paste that and then modify it to load the modules, activate the environment, and run our code. First we load the Python module, and we'll also need a CUDA cuDNN module, which I'll come back to shortly. Then here I am adding a command to source the virtual environment. I'm using the full path to the virtualenv I created, but you can also use the relative path name if you wish. Then we add the command to run the pyTorch script with Python. Now you may remember that when I visited the pyTorch website, I chose the instructions for the pyTorch version corresponding to CUDA version 11.6. I'm going to find the relevant CUDA cuDNN module on the cluster. Here we see that there's one available for CUDA 11.6, so although it's the default version, I'm going to specify the version number in my script so that it continues to use this version even if the default version is changed by the cluster admins in future. Now, a quick word about the resources required for the job. They're pretty much standard for GPU jobs, so for a single GPU we're going to specify 8 cores and 11 gigs of RAM, and we'll also ask for the Andrena cluster to be used. Now that we've prepared our job script, we can submit it to the scheduler using the qsub command and the name of the job script. The job will enter the queue and will be executed when resources are available. We can see the job has now started running and it's being executed on SBG10. We can connect to this node and check the status of the GPUs. Here, my code is using GPU device 3 and it's a very simple script, so it only uses about 3% of the GPU. In real world scenarios, it will be much nearer to 100%. Our job gets exclusive use of this GPU, and you can also see how much GPU RAM is being used out of a possible 40 GB on this GPU. Press Ctrl C to exit this view. This example job is a very short one. The job is already completed and we can see that the GPU device 3 has been released and it's now available for another job to run. The job produced some output. Now let's inspect the output from the job. Notice that the suffix is the same as the unique job ID that was shown in the qstat command earlier on. The results look correct, and my example script also included some debugging commands to print which device was being used before and after the GPU was activated in the Python code. Now if any errors were produced in the process of running the code, then they would also appear in this output too.